All right, guys. So today's topic is dislocations in FCC crystal structure. So what do you guys understand? What do you guys imagine when I say FCC crystal structure? What are the properties of FCC crystal structure? Any idea? Do you guys remember what is FCC?
We have 4 atoms in total in a cube, hocam.
You said 4 atoms per unit cell, right?
Yes, hocam.
So at each phase, we have half an atom plus 1/8 atom at every corner. So this is the number of corners of unit cell and the number of phases. What else? In total, we have 4. What else? What else?
74% of the total unit volume is occupied by the atoms.
Perfect. So atomic packing factor. How can we calculate the atomic packing factor? Do you remember? Ramazan, do you remember how to calculate the atomic packing factor?
No, hocam. I'm not knowing.
Anyone? Anyone wants to contribute? Okay, let me just quickly remind
Hocam,
you.
Can I?
Number? Yeah, please, Ahmed.
I think it is the volume of atoms over the unit cell volume.
Perfect. Unit cell volume. The volume of unit cell. Number of atoms per unit cell times the volume of atoms, right? So for FCC, we have in total 4 atoms per unit cell. How about the unit cell volume? If you consider the lattice parameter as A, the volume of unit cell is nothing but A cube, right? It's a cube. And the lattice constant is A, and the unit cell volume is A cube. How about the volume of the atoms? The volume of the atoms. We need to relate the atomic radius R with somehow we need to relate it with the lattice constant, right? So do you guys remember the representation of FCC?
Hocam, we should use face diagonal and shape diagonal.
Perfect, perfect. So remind me how to do that.
Let's start from the right upper corner, hocam.
So this is the lattice constant A.
Mhm.
This is lattice constant A. And each corner we have 1/8 atom, right? And
Yes.
at the face, we have half an atom. Perfect. So what to do next? You set the diagonal. The diagonal is nothing but a square root of 2. And it is equal to what? Ahmed?
4R hocam.
Perfect. So actually the representation is like this, right? One R here, two R here, another R here. So it is equal to 4R. Then you can relate the radius with lattice constant, which is R is a square root of 2 divided by 4. Then just 4 over 3 pi R cube square root 2a divided by 4 cube. And we have 4 atom here divided by a cube. What is the answer for FCC? Do you guys remember what is the atomic? 0.74, right? Is it correct?
Yes, hocam.
Perfect. FCC atomic packing factor is 0.74. How about simple cubic? What's the atomic packing factor? For simple cubic, let's do it quickly. So at each corner, we have an 1/8 atom. So R, 2R is equal to 1 lattice constant. And for simple cubic, we have only 1 atom per unit cell. 4 over 3 pi A over 2 cube divided by A cube. The answer should be 0.52. And who can do it for BCC? So this is for simple cubic. Don't forget, we have only 1 simple cubic material in the nature, and Madame Curie found it. What was the name of simple cubic element? The only one. Only simple cubic element. Simple cubic crystal structure. Roa, do you remember the simple cubic crystal structure element, the only one?
I'm sorry, no, I don't.
How about Ahmet Hakan?
Hocam, I just checked it from the internet. I think it is polonium.
Perfect. It is the only element who has a simple cubic crystal structure. Okay, how about body-centered cubic? Atomic packing factor. Just tell me the relationship between the lattice constant A versus the atomic radius R. We have a big atom at the body, and we have 1/8 atoms at the corners. First, you need to find one diagonal, which is this guy right here. Then, using this lattice constant and this diagonal, you can find. So let me use different color. So this part, or this part, is A square root of 2, right? And we have another A here. And the total diagonal of the unit cell is nothing but A square root of 3. Is it correct?
Yes, hocam.
And it is equal to 4R, right? Then you can calculate the atomic packing factor of BCC. Just check and tell me the number. So this is for FCC. Simple cubic should be 52. For BCC should
60.
be around 60.
8 hocam.
68. All right. So once you compare FCC, BCC, and simple cubic in terms of atomic packing factor, how can you conclude which one is the most dense crystal structure?
FCC. Since
FCC, right? So FCC, it is dense. Atomic packing factor is 0.74, and it is a dense crystal structure. What else? Give me some example of elements. Some elements.
Gold
Maybe
and silver.
gold, silver, perfect. Silver, gold, or maybe copper, right? Or aluminum, nickel, and their alloys. And if you think pure silver, pure gold, think about the pure gold, like the quarter of the gold. Is it a hard material or you can easily bend it? Is it a soft material? So what do you think? It's a soft or very strong hard material?
I think it's soft hocam.
Erşan,
we
you
can-
think it's soft.
Yeah.
How about
You can easily bend.
Ramazan, Kaan, Resul, Roa? Do you guys all agree?
Yes, I think it's soft when it's pure, but if you add copper, then it gets harder.
Perfect answer, Roa. So basically, they are very soft material. So dislocations move very easily. And the critical resource shear stress values for the single crystal is in between maybe 0.1 to 1, 0.1 to 1 megapascal. So it's very, very soft. It's very, very soft. But they're ductile, right? But we need to harden them. We need to increase their hardening, their strength levels. So if you look at the stress and strain diagrams of FCC, what you're gonna see is something like this, whereas the BCC, so this is BCC, and this is the FCC stress versus strain curve. The difference is due to dislocation motion. So this course, we're gonna analyze the dislocations in FCC metals. So FCC, let's remember again. So each unit cell consists how many planes in the crystal structure?
6.
Not 6, but we have only 1, planes, but we don't have 6. We should have
3.
3 direction, not the plane. Glide plane is nothing but just the tangent vector by the Burgers vector. Basically, it consists of 4 1, plane. All the planes are 1, planes. You can basically throw the tetrahedral and you can see the planes. And each 1, plane, planes they consist three 1, 1, 0 directions. 1, 1, 0 directions. Therefore, there are 12 slip systems in FCC. So 12 is not that much because in BCC, we have 48 slip systems. 48 slip systems in BCC. But remember again, we said FCC is more ductile than BCC. How can it be possible? We have 12 in FCC, and for hexagonal closed pack, we have 36. 36 hexagonal closed pack slip system. So how can it be possible? Think about the dislocations. Think about the movement of dislocations. So FCC is the smallest slip system in terms of numbers, but it is the softest and the most ductile one. What could be the explanation? Any idea? Roa, do you have any idea what could be the explanation? So the plastic deformation are due to dislocation motion.
I think it's because of the packing factor.
You said maybe the packing factor, atomic packing factor. So FCC is dense. Maybe, yeah, like somehow related with the packing factor, but not totally. Any other idea, Khan? Maybe you can help me at this point.
Can you ask me again, Hocam?
The idea is, Khan, the question is, we have only 12 slip systems in FCC and 48 slip systems in BCC. But FCC is more ductile than BCC. What could be the explanation?
Hocam, maybe the distance between atoms affect this, I think.
You're also mentioning about the packing factor.
Yes, yeah.
Actually, it's good. Actually, it's good because the distance between atoms and the atomic packing factors create the lattice resistance. And the lattice resistance is due to the necessity to make and break the bonds at the core of the dislocation every time it moves an atomic distance. So dislocation moves an atomic distance and it needs to breaks the bond and make the bond. And the lattice resistance is due to the necessity of breaking and making the bonds. And the lattice resistance of FCC is very small. So it is known as perilous stress. The perilous resistance, the perilous barrier of FCC, it is very, very low. For FCC, the bonding is rather non-directional, but BCC, directional. So the main answer is for FCC, think about the plastic deformation. We have more dislocation activity, right? More
Yes.
dislocation, basically. And for BCC, we have less dislocations. It is due to the fact that the lattice resistance is so low in FCC, so that dislocations can move very easily in FCC. Whereas in BCC, it is really, really hard to move the dislocations. BCC, for example, tungsten, zirconium, right? It's very, like the transition, most of the transition metals, it's hard to move to dislocation. All right, any questions so far? Then the next question of mine, again, the properties of FCC. Remind me the stacking sequence of the FCC. What is the stacking sequence? In terms of planes. Do you guys remember A, B, C planes? Like we had a center cubic. We had an atom here, another atom at the face, another atom at the other corner, and we had A, B, and C planes, right? So what was the stacking sequence in FCC?
A, B, C, A, B, C. It goes
Goes
like
like A's, B's, and C's, right? Let me draw in 2D. This is also 2D, but I wanna rather draw it in this way. So we have A plane, A plane, A plane, B, 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 C, C, C. Then we have atoms on these planes. A. The starting point is different. So for example, A starts from here, B starts from here. B, B, B. B, B, B atoms. Let me just quickly draw them. And the stacking sequence, sorry. Is A, B, C, A, B, C. But do you think the atomic alignment is perfect? Like, think about how we cast the materials. So basically, it happens at very high temperatures, maybe 1,000 degrees, right? So during cooling or at high temperatures, we could have some voids. For example, let's suppose we have a void here. All right, what happens if we have a void at this particular location? Basically, what is gonna happen is this plane, the B plane, will try to attract the other planes, the first neighbors, firstly. So this plane will shape something like this. And this plane will shape this way. And also, this plane will be disoriented, something like this. And we will have some faults, some stacking faults. So if the stacking sequence change from ABC to BCA, we have a stacking fault at this particular point. And stacking fault is inversely proportional with stacking fault energy. And the stacking fault energy dictates the deformation modes, if we are doing phase transformation or slip or swinging. So it is very important for deformation. Dictates the deformation mode. Perfect, perfect. Before going to what kind of dislocations do we observe in FCC, I want to also discuss the energy of dislocations. What was the dislocation energy? You should remember this from the previous class or the reading that I put on Canvas system. How can we calculate the energy of dislocations? Energy of dislocations. Resul, do you remember the energy of dislocation?
I remember the concept, but I don't remember the way we calculated it.
I see. So how can we divide what are the two main components of the energy, dislocation energy? So this is the total energy per unit length. Total energy per unit length. What are the two main components?
Burgers vector.
Not Burgers. So it is related to Burgers vector. I agree. I totally agree. It's a correct answer, but the answer I'm looking for the main contributors. One is the energy contained in the elastic field, right? Elastic energy plus the energy in the core, right? the core energy. So we have like a bunch of formulas calculating the strain energy for a volume element. And basically, at the end of lots of calculations, the elastic energy of screw dislocation is is there anyone who remembers the elastic energy of screw dislocation? Maybe you can remember from your GB square. So let me write.
Over 4 pi.
Perfect.
1 minus
ln r divided by r0. Or let's write not capital but small. How about the elastic energy of edge dislocation? It's very similar, but this time we have another term. 1 minus Poisson's ratio. Again, ln r divided by r0. So which one? So apart from this term, they are same. And the Poisson's ratio for metals, it's around 0.33. So compare the elastic energy of screw and edge dislocations. Which one is smaller? Which one is smaller? Just looking at these formulas.
H.
Do you think edge is smaller?
Screw is small.
Right? We have like here, we will have something like 0.67, which will increase the nominator part of the edge dislocation. Therefore, edge is larger, edge is greater. Basically, the relationship between them is energy of screw dislocation is maybe 0.66 times the energy of edge dislocations. And the core energy is again proportional with GB square divided by 2 pi. So in total, energy of edge and screw, total energy is some constant times GB square. In short, it's related to Berger's vector. You were right. So it is proportional with Berger's vector square. So this is very important. So we will use this term while examining the dislocations in FCC, BCC, or HCP. So this is very important. Don't forget. Energy of dislocations is proportional with Berger's vector square. So any questions so far? Any question? If not, I'll just stop at this point for 10 minutes and I'll see you guys after the break. All right, let's continue. We said FCC, we have 4 1-1-1 planes. So this is 1-1-1 plane. Plane is 1-1-1. And what was the direction of Berger's vector? What was the Berger's vector direction? Anyone? Roa, do you remember the direction of Burgers vector?
No, I actually, because I didn't attend last class.
No, we just mentioned it. We had 4, 1, 1, 1 planes.
1, 1, 0 was it hocam?
Right? 4, 1, 1, 1 planes and 3, 1, 1, 0 direction. So please remember this. 4, 1, 1, 1 planes and 3, 1, 1, 0 direction. So this is the dislocation. 1 over 2, 1, 1, 0. Since the edge dislocation is just the introduction of extra half plane, we call it 1 by 2. Or suppose the length is A, we can also call A by 2. So in FCC crystal structure, the edge dislocation cannot remain as a single edge dislocation. After we move the edge dislocation, they decompose into some partials that we call Shockley partials. And the Shockley partial is these partials, and they are 1 by 6 2, 1, 1 direction. So they are 2, 1, 1. So remember the Franck's rule. Franck's rule states that the energy is proportional with the Burgers vector square. Energy is proportional with Burgers vector square. And in between these Shockley partials, we have stacking faults. So the total reaction is something like this. 1 over 2, the edge dislocation, our first dislocation, 1, 1, 0, dissociates into 2 parts. One is 1, 1, 6, correct? 1 over 6, 2, 1, 1, 2, 1, 1, plus, again, 1 over 6, 1, 2, minus 1. Is it correct? 2 by 6 is 1 over 3. Sorry, this is not correct. No, 2 over 6 plus 1 over 6 is 3 by 6. So this 3 is just 3 by 6, which is equal to 1 by 2. Let's check the other term. 1 by 6 plus 2 by 6, again, 1 by 2. 1 by 6 minus 1 by 6 is equal to 0. Perfect. Of course, we have a stacking fault energy after this reaction, after this dissociation into 2 parts. So
Can I ask something before that?
Go ahead.
Like we said, like it is 1 over 6, 2, 1, 1, and in the second one, it is 1 over 6, 1, 2, 1. I didn't get this part actually.
So this is the family, 2, 1, 1 family. Sorry. All right, guys, can you tell me if this reaction is energetically favorable or not? Just calculate the energy of this part and the energy of the second part and check if it's energetically favorable or not. So this is kind of very small quiz. Let's do it all together. The question is, we are saying that in FCC, once we have an H dislocation, which is A over 2, 1, 1, 0, they dissipate into two different Shockley partials. Let me draw it with different color. 1/6 or A/6, 1, 1, 2 family. So this is the family. This can be 2, 1, 1, 2, 1, -1. This is the family of the direction. And the length is A. So if the dislocation is something like this, the length of this one is B. We call it B/6. And the question is, if the reaction of A over 2, 1, 1, 0 to A over 6, 1, 1, 2 plus another A over 6 to 1, sorry, let me just go back and check. 1, 2, -1, right? 1, 2, -1 plus the Stekenfold energy. The question is just check if it is energetically favorable or not. I'll give you guys 5 minutes. All right, any answer? Did you guys find if it's energetically favorable or not?
Not hocam.
Why not? Tell me the reason, Ramazan.
Because it's not equal. When we look at the left side of the equation,
Okay.
it gets me to A over 2, and 0.
All right.
When I look the right side, in the first part, it gets me A over 3, because A over 6 times 1 and A over 6 times 1 give me A over 3.
Okay.
Not equal to the left side. But the other two part is equal. Since one of the parts is not equal to the left side, it's not energetically favorable.
Anyone with an answer of energetically favorable?
Hocam, I found favorable. So like when I
Listen,
do,
can you explain?
yeah, when I do the calculation, I find that the right side equals to the left side. So yeah, that's the reason why I say it's favorable, actually.
Let me give you guys 2 more minutes and think about it. You guys think about it. All right, let's do it together. What is the energy of this part?
A over 2.
So we have, let's normalize them. Let's say this is not A, but 1, 1, and 1. So the energy is just proportional with B squared, right? So I take the square of this B. So this is 1/4, 1 square plus 1 square plus 0 square, which is equal to 1 plus 1, 2, 2 over 4, which is 1/2. So the left-hand side, the energy is 1/2. How about the right-hand side? Tell me the energy of right-hand side. Come on, guys. Tell me the energy of right-hand side. Tell me the energy of this part. Kaan?
Yes, hocam, I'm here.
just tell me the energy of this guy right here. So anyone who can tell the energy of this part?
1/6.
1/. So we are taking b square, not 6, right? 1/6 square is 1/36. Okay.
1 plus 1 plus 4.
1 square plus 1 square plus 2 square, which is 4, 5, 6. 6 by 36 is 1/8. So the energy of this part is 1/8. How about the energy of second part?
Again, hocam, can we say it is 1/8?
Same, right? 1/6. So 1/6 plus 1/6 is 1/3. So do you think it is energetically favorable or not?
Not favorable, hocam.
Why not? So 1/2 is greater than 1/3. So the dislocation wants to go to lower energy levels. So why not? It's energetically favorable. So this part is very important, guys. So in FCC, you have to understand this example. So let's do it all together, and please pay attention.
Can I ask
Okay,
something?
please go ahead.
We had a sign on the top of 1. I wonder what is it?
So that means negative, -1. But if you take the square root of -1, again, you will find 1.
Okay, I see.
Okay, guys, please pay attention. And I want you to understand this part. This is very important if you want to understand the dislocations in FCC and strengthening mechanisms in FCC. So FCC, they differ by edge dislocations. And edge dislocation, the representation is 1/2, 1, 1, 0. But the idea is, so this is the plane of 1, 1, 1. And the edge dislocation is just 1/2, 1, 1, 0. We say that once we give small loading to the system, edge dislocation dissipates into 2 main parts, the partials, Shockley partials, or Frank partials. We will talk about Frank partials later. But the Shockley partials are the dislocations, and they are 1/6, and the direction is 2, 1, 1, the direction family. And in between them, we have a stacking fault energy, which is the penalty that we pay while dissipating edge dislocation into 2 Shockley partials. So this is the stacking fault energy, the penalty that we pay. So let's check the reaction. One by 2 edge dislocation, 1, 1, 0, dissipate into 1/2, 2, 1, 1, plus, I just wanna, sorry, not 1/2, 1/6, right? 1/6, 2, 1, 1, plus 1/6. Let's check. Here, the first term is 1/2. Here we have 2/6. In order to make it equal, we need additional 1/6. So this term is 1. The second term, again, we have 1 by 2. This term is 1 by 2, 1 by 6. We need 2 by 6. So the second term is 2. Here we have 0. Here we have 1 by 6. We need minus 1 by 6. Therefore, this part is minus 1. Is it clear so far?
Yes, hocam.
Guys, please give me some feedback. Is it clear?
Yes, hocam. Clear.
Any question? Okay. So let me delete this part and just leave the reaction. And the penalty that we pay is stacking fault energy. And we are checking if B1 square is greater than B2 square plus B3 square. So let's call it B1, B2, and B3. Right? If B1 square is greater than the summation of B2 square and B3 square, the dislocation will dissipate. The reaction will be energetically favorable. To calculate B1 square, we use the Frank's rule. Energy is equal to B square. So the square of this part is 1 over 2 square, which is 1 by 4. 1 square plus 1 square plus 0 square, which is equal to 2 by 4, which is 1 by 2. So this is B1 square. Tell me B2 square. What is B2 square? Roa, can you help me to find B2 square?
It's going to be 1 square plus 2 square plus 1 square.
And what is the square of this constant? You need to take the square of this constant first. 1 by 6 square is 1 by
1 over 36.
36, perfect. 2 square plus 1 square plus 1 square. So it is B2 square is equal to 4, 5, 6. 6 divided by 36 is 1 by 6. Khan, help me to calculate B3 square. Khan?
Yes, hocam.
Can you help me to find B3 square?
Sure. We need to multiply with 1 over 6 times is true.
Okay, just tell me, what is it?
1 over 6 times. Actually, I didn't understand very well, but I'm trying to understand this.
So if you don't understand, just don't hesitate to ask. Just ask me. So basically, if you have a constant and your Burgers vector A, B, C, and this is B, B square, it's nothing but C square times A square plus B square plus C square. So thinking about this equation, just try to calculate the square of this dislocation.
Okay, 1 over 36 times
1 over 36 times, perfect.
1 plus
1
4
plus
plus 1.
4 plus 1. Okay. So it is
1 over 6.
over 6.
Yes.
So B1 square is 1 by 2. B2 square is 1 by 6. And B3 square is 1 by 6 again. So we are checking B1 square is greater than B2 square plus B3 square or not. 1 over 2 is greater than 1 by 6 plus 1 by 6. So 1 over 2 is greater than 1 by 3. So this equation is energetically favorable. That means if we have an edge dislocation in FCC, they will dissipate into two main dislocations, which are Shockley partials. 1 over 6, 1, 1, 2 slip system. All right?
Yes, hocam.
Perfect, perfect. Okay, in terms of partial dislocations, so these are partials. We can have Shockley partials. They are called Shockley partials. Or we can have Frank partials. Basically, Shockley partials, they are formed by splitting a perfect dislocation. So this is perfect dislocation. Once we split them, we form a Shockley partial. Kaan Eryilmaz, can you please mute your microphone?
Sure.
And the Frank's partial, they are formed by inserting or partly removing the 1, 1, 1 plane. If you remove the plane, you will create a stack and fold, which will create some immobile dislocation. Don't forget, Shockley partials are mobile dislocations. They are mobile, and 1 over 6, 2, 1, 1. They are mobile. They're formed by splitting perfect dislocation. Frank partials, they are immobile. They are formed by removing or inserting a 1, 1, 1 plane. And their representation is nothing but 1 over 3, 1, 1, 1. So the question is, all right, we have Shockley partials. Edge dislocation goes into the Shockley partials. What is next? What can happen next? These dislocations are coming here. Then we have another plane, right? Let me draw a new figure. Oops, I need to delete some of the pages. I reached the maximum number of pages. Clear all my drawings. Okay. Clear, 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 clear. Clear. Done. Okay. Suppose we have 1 by 1, 1, 1 plane. This is the first 1, 1, 1 plane. We have 4 1, 1, 1 planes, don't forget. Then we have another 1, 1, 1 plane here. This is another 1, 1, 1 plane. We have an edge dislocation, and we apply shear stress to edge dislocation. So this is, what is the direction of an edge dislocation? The original perfect edge dislocation. What was the Burgers vector? Anyone? What was the Burgers vector of an edge dislocation? Resul?
I don't remember hocam.
Roa, do you remember the direction of an edge dislocation? The perfect edge dislocation without going into the Shockley partials.
No, we don't.
Anyone? So like the question is simple. I asked it like 2, 3 times before.
110 was it hocam?
Of course. Don't remember, this is the main part. In FCC, we have the planes in 111 direction, and the direction of a dislocation is 110. This is how we start. Once we apply some shear stress, what will happen? Kaan, what will happen to this edge dislocation? So the original one is perfect edge. 1/2, 110. Kaan, what will happen?
Actually, energy will increase, I think.
Okay. Then, do you think this edge dislocation will go there and it will glide as an perfect edge dislocation, or it will dissipate into some dislocations?
It will dissipate in some dislocations, I think.
Perfect. So edge will dissipate into the partials, either Frank partial or Shockley partial. Let's investigate Shockley partials first. Shockley partial. And tell me the Burgers vector of Shockley partial. Ahmet Enes, what is the Burgers vector of Shockley partial?
110 again.
Do you guys remember the example we just solved?
Yes, 1/6, 211.
And you guys all told me that you get the example. If you have any question, guys, if you don't understand, please ask. You don't ask anything and it comes up that you don't remember what we just discussed. So this is 1/6, 2, 1, 1. This is the Shockley partial. Again, this is 1/6, 2, 1, 1. Okay, it continues its motion and comes to here. So what can happen is basically it may move to the other plane. But the thing is, Shockley partial cannot move into the other 111 plane. Only the perfect dislocation can move to other plane. Therefore, after second step, the one part of Shockley partial will be here, or let me draw with different color. This is the one part of Shockley dislocation. The other one will reach the Shockley dislocation, and they will create, again, the edge dislocation, this part. And this part will go to the other plane, like this. So this is an dislocation, perfect dislocation. And of course, it will dissipate again into Shockley partials. Don't forget, Shockley partial itself cannot pass through the other plane, cannot jump to the other plane. They need to catch each other, create either the screw segment and create a full dislocation. Then the full dislocation, perfect dislocation, can jump into the other plane. Perfect. This is called as cross slip. This is cross slip. And it is one of the main mechanisms in FCC. Perfect, perfect. Any questions so far? If you have any question, guys, I insist, please ask it. Please try to ask. Any question? No? All right. So this is very important, guys. All right. Another scenario. We have one plane. One plane. We have another plane. All right. So let's think. Let me ask again. What is this plane? What is the plane of FCC? What is the main plane of FCC?
111.
111. Always 111. This is 111 plane. This is another 111 plane. And edge dislocation, perfect edge dislocation. What is the Burgers vector of perfect edge dislocation?
110.
110, perfect. So far, so good. Suppose we have one perfect dislocation at 111 plane, another perfect dislocation. This is again 1/2, 111. Suppose we apply a shear stress. Shear stress will be applied. Then what will happen to this edge dislocation? Again, what will happen to these edge dislocations?
They will split into partials, will they?
Roa, do you remember what's gonna happen to these edge dislocations?
You're gonna be the Shockley partial dislocation?
Perfect. We will form some Shockley partials, and in between Shockley partials, we will have some stacking faults. So this is 1/6, 2, 1, 1. And another Shockley partial, 1/6, 1, 1, 1. Okay, this point is very, very important, guys. Very, very important. This Shockley partial and this Shockley partial, they meet at this intersection. This junction is called as Lomer Cottrell junction. They meet at this Lomer Cottrell junction and they create another dislocation, which is called as stair-rod dislocations. So two Shockley partials come together and they create the stair-rod dislocations. Let me draw stair-rod with black. This is stair-rod dislocation. And the equation, the Burgers vector is 1, 1, 0. Do you think this is energetically favorable? Let's check. We are saying that two Shockley partials, 1/6, 2, 1, 1, and another 1/6 Shockley partial, they come together and create a stair rod dislocation. 1, 1, 0. So for this reaction, we need -1 here. We need 1/6, 1/6. So this is gonna be, what should be the reaction here? Again, -1, correct?
0.
0 hocam.
So this is 0, but this cannot be Shockley partial. So what should we do in this case? What should we write for this reaction? Suppose 2 Shockley partial comes together and create a stair rod. What is the reaction? Can you guys help me to writing the reaction? What is the reaction? So this cannot happen. This is something weird. How about, for example, 1/6? Think about -1, -2, +1, plus 1/6, 2, 1, and -1. What do we create? (1/6) -1 plus 2/6 is just 1/6, right? -2/6 plus 1/6 is -1/6, correct?
Yes.
Yes.
And this is 0. Is it correct?
Yes.
Perfect. So now we found the reaction. So 2 Shockley partials come together and they create, so this is first, Shockley partial, another Shockley partial, they come together at the lower cultural junction and they create the stair rod dislocation. So let's check if this reaction is energetically favorable or not.
But I actually don't get, why did we put negatives?
Say it again, Roa.
Like for the first Shockley partial, there we have like negative numbers now.
Right, like these Berger's vector directions are the families. If we are saying the full edge dislocation is 1, 1, 0, for example, this is the family. It can be 1, -1, 0, or it can be 0, 1, 1, 0, 1, -1. So the direction, if you look at the tetrahedral, like the Thomson tetrahedral, you will see some directions. Let me try to find the Thomson tetrahedral and show it to you in Google. Let me just Google the, or maybe I can try to draw by myself. So let's define a coordinate system. So let's define this as 1, 0, 0, x-axis, 0, 1, 0, and 0, 0, 1 along Z. 0, 0, 1. So let's get some points and create our cube. Let's create our cube. Dum, dum, dum. Good, good. So I'll just try to do this. This and this. Like, this is not the best drawing, but like this is. So this is the best I can do with hand. So let's define the 1, 1, 1 plane. So I'll just cut this part, and this part. This is 1, 1, 1, 1 plane. 1, 1, 1 plane. So we have different directions here. This one is 0, -1, 1 direction. Right? Think about it. We come from here to here. So from here to here, we go minus direction along y-axis. From x, it's 0. From y is this guy right here. From here to here, we go -1, right? This is -1, and we go up by +1. Is it clear, Roa?
Yes.
So along x, we don't change anything. We don't go this way. This is 0. Along y, from here to here, we go in negative direction. And from bottom to up, we go +1 z direction. Therefore, it is 0, -1, oops, 1. So tell me the Burgers vector of, for example, let's say this guy right here. So let's say this is the first Burgers vector, this is the second Burgers vector. Along x, we go -1, right?
Yes, it's going to be -1, 1, and 1.
-1, 1. Do you think, do we go along z-axis?
0, 0, 0.
0, right? -1, 1, and 0. How about this guy right here? We are at the y-axis, so +1, right? 1, 0, and -1. This is basically just the representation of the 3 direction of 1, 1, 1. So we are talking about 1, 1, 0 slip families, and this could be any of these. Any of these. All right, let me go back. Thank you, Ra, for asking this question. This is very important for you to understand. Okay, 2 Shockley partials meet at the junction, Lomer-Cottrell junction, and they create the stair rod. Do you think this is energetically favorable? Tell me. So we are checking B1 square plus B2 square is greater than B3 square or not. So tell me the energy of B1 square. Tell me the energy of B1 square, guys.
1/6 hocam.
1/6. Tell me the B1 square.
Again, 1/6.
What do you mean by 1/6?
Like B1 square is equal to 1/6 and B2.
Okay, don't tell me the result. Just let's go. Let's do it simpler. 1/36 plus 1 square plus minus 1 square plus minus 2 square plus 1 square. Correct? Which is 1/6, as your friend suggested. The result is 1/6 plus another 1/6. And what is the energy of this part?
1/18 hocam. If I'm not mistaken.
1/18. Perfect. So do you think 1/3 is greater than 1/18? Do you think this reaction is energetically favorable or not?
Favorable hocam.
Roa, what do you think? This is energetically favorable or not?
Favorable.
Everyone agrees?
Oh, sorry, it should be the opposite side, right? Because we're looking for the SR.
We are looking for the SR, right? Two Shockley partials come together and they create stay rod. The summation of the energies of Shockley partials are 1/3 and the stay rod is 1/18. So the formation of stay rods from these Shockley partials are energetically extremely favorable, extremely favorable. This is way greater than 1/18. So once they meet at the junction, at the Lomer-Cottrell junction, they form the stay rod dislocations. And the reverse of this reaction is too hard. You need to pay a lot of penalty. You need to give a lot of energy to reverse this reaction. That is why we have some pinning at this Lomer-Cottrell junction. And this pinning creates the hardening in FCC crystal structure. So they shock the partial, they form stay rods at the Lomer-Cottrell junctions, and we have some pinning. We have some lock, and this lock creates the hardening for FCC crystal structure. So is it clear? This is the main mechanism why we see hardening for FCC crystal structure. Is it clear, guys? This is very important point. If you didn't understand anything, please ask. So let's summarize what have we learned today's class. And just ask me if you didn't learn the outcomes of today's class. What have we Come, tell me something you learned from today's class.
Unit cell, maybe atomic package factor. I remembered it again.
What? So unit cell.
Atomic package factor.
Packing factor. So if you compare the atomic packing factor of FCC, BCC, and HCP, which one is the most dense crystal structure?
I think FCC is most dense.
Okay,
Is it true?
correct. Ahmet Enes Özer'den, please tell me something you learned from today's class.
FCC planes are 111 and the vectors are 110.
FCC, great. The main plane is 111 and the direction is Berger's vector is 110. Perfect. Ahmet Hakan, tell me something you learned from today's class.
Sure, hocam. We learned Shockley partial, which includes mobile dislocations.
Perfect, perfect. So edge dislocation, due to energetic region, they go into Shockley partials. And the Shockley partials, the Berger's vector is along 1-1 or 2-1-1 direction. Shockley partial. Erşat Mutlu, tell me something you learned from today's class.
So how can we decide if favorable energy? Like, how can
So
we
we
calculate
learned
it?
the Frank's rule. It says that the energy of dislocation is proportional with Berger's vector square. All right, Ramazan Ünal, tell me something you learned from today's class.
When two Shockley partial connect in a corner, normal quadruple junctions happen.
Perfect. Shockley partial plus Shockley partial, we create stair rod dislocations, which is the main source of hardening in FCC. Sorry, FCC. Resul, tell me something you learned from today's class.
So in FCC, the lattice resistance is so low, hocam, so such that the dislocations can move easily.
Perfect. They are soft due to lattice. This is very good point. Lattice resistance is so small. So small. Roa,
Yes, hocam.
last thing you learned from today's class. I'm sorry, you are the unlucky one. You're at
Yeah. I think I can say that the main mechanism in FCC are the cross slips.
All right, perfect. We also have some cross slip process. So H goes to Shockley partials. Shockley partials come together to form maybe screw parts. Screw parts. They went to another plane and they dissipate into, again, Shockley partials. This is called as cross slip, another plastic deformation mechanism. Perfect, guys. I think, yeah, you did very, very good. Is there anything you want to add?
Hocam, can we say, like, as a result of, for example, lower lateral junctional, we have a stronger dislocation at the end?
If we have more pinning, that means we have more hardening. Anything that blocks the movement of dislocation, this could be impurity, this could be void, this could be another solute atom. Anything that blocks the movement of dislocation is an hardening mechanism, extra hardening mechanism.
Thank you, hocam.
The more pinning points you have, the more hardening you will see in the material. Perfect. I think if you don't have any more questions, I'll see you guys next week.